everyone, welcome back to the population ecology lecture series. So now we're going to actually start going into these Lotka Volterra models of predator-prey dynamics. And as a starting point, we just have the model assumptions here on my right-hand side, which are first that prey populations have density-independent growth. So they're only limited by predators, and the same is true for predators, are only limited by prey. The third assumption of these models is that both prey and predators reproduce continuously, so we don't have those discrete population growth models. And finally, predation rate is directly proportional to encounter rate, meaning that if a predator bumps into a prey, that predation event occurs. Just to note, I will be using N to denote prey populations, not V. V is what Gatelli uses, so if you've been reading your book and looking at these models, they use V. But populace uses N, so I want to be consistent with populace. And then P is going to equal the predator populations. So if we go over here to the actual mathematical models, you can see that if we're looking at prey on their own with no predators, we have our simple population growth rate. R1 times N, when R1 is the per capita growth rate of the prey and N is that population size. Density independent growth. Now predators without prey are a little different. dP over dt is equal to negative d2 times P. So P is again the population size of the predator, and this negative d2 is the starvation rate of the predators. So the more they starve, the less their population will grow, and that's why that's a negative rate. Okay, so then we need to add in interactions between predators and prey using the chance of encounter. So the chance of encounter, those are two words. Chance of encounter is equal to CNP, where C is the number of prey a predator can eat. So this is a consumption metric like we were looking at in our resource-based models. If you're following along with Gatelli, they call that alpha. N we already know. P we already know, right? We got the population size of the prey and the population size of the predator. So, room here. Cn is the linear functional response of the predator to prey. We're going to be talking about functional responses at the end of this lecture series of predator-prey dynamics, but just keep in mind that right now what we're talking about is a linear response. So adding one prey has a linear effect on the predator populations. Okay, so let's add in that CNP here. For the prey, that just means we decrease their population growth by this encounter rate. For predators, it's instead adding their population growth, which makes sense. And what we do is we call this plus GCN. Now remember, CN is that linear functional response of the predator to the prey, and G is the per capita conversion. That's an arrow. of prey to energy. So, like many of our population models, what we're really interested in is understanding what's happening at equilibrium. So mathematically, at equilibrium, we have the following. I'm just going to separate that out here. Okay, so if we're looking at the equilibrium populations of predators and prey, we can start with prey and say n star, the equilibrium population size, is going to equal D2 divided by GC. So you can see that the size of the prey population is completely defined by aspects of the predator's population growth model, this D2 GC. Okay, in the same way, we have a predator population at equilibrium that is equal to R1, oops, that's a 1, R1 divided by C. So the predator populations are defined by aspects of the prey's population growth. So we're looking at the per capita growth and the number of prey the predators capture. Okay, so now we can look at the model in populace. So why don't you go ahead and pull up your populace, and I'll be right back with you.